Something pretty fundamental in math, solving polynomial equations, specifically the tricky ones.
Yeah, the really high degree ones, like the 13th degree equation you sent over.
Exactly. Now, for anything past degree 4, finding those perfect, exact symbolic answers, that gets tough with standard methods.
It really does. You often end up using computers for numerical approximations, just getting close.
Right. Because of things like, well, Abel's theorem, which basically says there isn't a general formula using radicals like square roots, cube roots for degree 5 or higher. Classical algebra hits a sort of limit there.
That's the standard picture. But this source material we're looking at today, from Professor Mourad Sultan Ezouidi, really makes a fascinating claim.
It does. It introduces something called Ezouidi's theorem. And the core idea, the really big claim, is that this theorem can actually find those exact symbolic solutions.
Yeah, a way around those classical limitations. It's
Yeah.
quite a statement.
And the source applies it to this specific 13th degree polynomial. Just looking at the coefficients shown, 13, 78, all the way down to 27, you can see it's not a simple case.
Not at all. It's complex.
And what the source highlights, like right away, is something interesting about this particular equation. It points out that x-1 is a root, but not just a root, it's a root with a multiplicity of 5.
Right. Multiplicity just meaning if you factor the whole thing out, that x1 factor would show up 5 times.
So 5 of the 13 roots are just 1.
Exactly. That's a key feature the source emphasizes for this specific polynomial.
Okay, so how does the source say this theorem, Ezouidi's method, actually works? How does it get these exact answers when others often can't?
Well, the approach described in the source, it kind of steps away from trying to find radical-based formulas. Instead, it uses let's call it a structured process.
It's structured process.
Yeah, focused on the polynomial's coefficients. The source talks about calculating a sequence of values. It labels them des k1.
Okay, so and how are those calculated?
It's recursive. So each value builds on the previous ones, and the calculation itself uses the polynomial's coefficients directly. The source uses a term 1 areos for parts derived from those coefficients, and also uses binomial coefficients.
Binomial coefficients, like from Pascal's triangle.
Exactly like those. So the formula, as presented, combines these polynomial coefficient terms and binomial coefficients in a specific recursive way to get these as values. It's like a systematic way to decode the root information hidden in the coefficients.
So it's not forcing it into an old formula structure, but analyzing the numbers differently. And the source stresses that this method is claimed to give exact answers.
Precisely. No approximations. The goal is the precise solvable symbolic roots. That's the core claim for this theorem.
And for this 13th degree example you sent, the source actually shows this calculation.
It does. It shows how applying this recursive formula to that polynomial plays out. And the results for those values are, well, quite striking according to the paper.
Striking how?
Most of them turn out to be 0. Just 0. Except for 2 of them. The source finds $739, and then there's us $12.
Wow, okay. So lots of zeros and then a couple of specific non-zero values involving powers of 13.
Right. And this specific pattern of Vell's values, the source explains, is what leads directly to figuring out the roots. It confirms the XEF1 root with multiplicity 5, like we mentioned, and it also apparently reveals the exact form of the other 8 roots. The source shows how these involve powers of 13, giving their precise symbolic form. It walks through verifying them.
So this brings us back to the bigger picture. We have a method presented in the source that's claimed to give exact algebraic solutions for these really complex polynomials.
The kind that classical theory often suggests aren't generally solvable by neat, exact formulas involving radicals.
It definitely makes you think, and maybe this is the question for you listening. If a new approach can find exact answers for problems we thought were fundamentally limited to approximations, or maybe even considered unsolvable in exact terms, what does that really mean?
Yeah. What are the broader implications? It certainly seems to challenge some long-held boundaries in algebra, at least based on what's presented in this source material, something to mull over